Hi everyone, this will just be a short video going over the most commonly missed questions from our L'Hopital quiz last week. So starting with the first most commonly missed one was number 4. And this was the problem here, limit as z goes to infinity of z squared plus e to the 4z divided by 2z minus e to the z. So technically you check first what the numerator and the denominator would be, or the size of each of them would be as you let z go to infinity. So it would kind of be like this. You'd have infinity squared plus e to the 4 times infinity all over 2 times infinity minus e to the infinity. So in the numerator, it's a really gigantic infinity because z squared is a higher degree than 2z, so this is definitely larger than that. And e to the 4 infinity is definitely larger than e to the 1 times infinity. But technically, you still have infinity in the denominator. It's just not as large. It's a smaller degree, smaller size, and it's also negative. But this is a situation where L'Hopital's rule could apply because it is one infinity divided by another one. So what we could do is take the derivative of the numerator and denominator with respect to z, because that's the variable that's approaching infinity. So if I did that, then I could take the limit as z approaches infinity of the derivative, 2z plus 4 times e to the 4z, if I use the chain rule. And then on the denominator, the derivative would be 2 minus 1 times e to the z. But both of those are still approaching infinity, right? I still have 2 times infinity plus 4 times e to the 4 infinity all over t minus infinity. So I could keep going. You can apply L'Hopital's rule repeatedly and just keep taking the derivative as long as the fraction still either follows 0 over 0 or infinity over infinity, which this does. They're still both infinitely large. And then the derivative of 2z would be 2, and then 4 times e to the 4z would be 16 e to the 4z, and then all of that's divided by negative e to the z. And I still have infinity over infinity, although maybe it's becoming more obvious to you that the numerator is definitely larger. So this limit is going to be approaching negative infinity. But I'm going to keep going using L'Hopital's rule. I'm going to continue taking the derivative of the numerator and the denominator. And so the numerator is now 64 e to the 4z all over negative e to the z. So I can simplify a little bit right here. I can think of negative e to the z as negative 1 times e to the z. 64 divided by negative 1, that would equal negative 64. And then e to the 4z divided by e to the z would equal e to the 3z, because you can subtract powers. 4z minus 1z is equal to 3z. So then this whole quantity turns into negative 64 times e to the 3z, and I'm letting z approach infinity. So if you do that, this would end up being negative 64 times e to the 3 times infinity, which is basically negative 64 times infinity, which is going to provide a large negative number, right? Negative infinity. So those of you that got it wrong tended to select positive infinity as the answer because you probably recognized that the size of the numerator, both the degree and the size of e to the 4z, were bigger than the denominator. So this is a classic big over small scenario. So remember, the answer to a limit as z goes to infinity where the numerator is bigger could be positive or negative infinity, and you'd have to kind of test a value just to see what would happen. So because this is subtracting e to the z in the denominator, and e to the z will always be bigger than 2z. Well, not always, but when z is approaching infinity, it's definitely bigger. E to the 100, for example, is larger than 2 times 100. This will overrule that. So when you subtract them like this, 2z minus e to the z, then that value will end up being negative. Meanwhile, the numerator is always positive. So you end up with a positive divided by a negative, and the value of it is getting larger and larger and larger. So it's approaching negative infinity. That's the logic behind it. That's how you could kind of determine that from looking just at the beginning. But now that we have learned L'Hopital's rule, you can just continue to take the derivative of the top and the bottom. As long as you have 0 over 0 or infinity over infinity, you can continue taking the derivative of the top over the bottom until you get to a point where it becomes really obvious. Okay, yeah, this is definitely approaching negative infinity as the variable z approaches positive infinity. So the next commonly missed question was number 7, and understandably so, because it's written in a very confusing way. And in fact, it's the first time you're having to look at an integral where the upper limit of integration is approaching infinity, right? Our x is approaching infinity. But I like to encourage you that even when things look different or confusing, to still try to reason through what might be happening to the value of this integral as the upper limit goes to infinity. But first, let's take a look inside at this function, natural log of e to the power of 4t minus 1. So let's consider this natural log, right? Natural log of something, of x. Well, that's the same thing as a log base e of x, okay? So I've got a log base e of e to the power of 4t minus 1. So this ln and log base e and e to a power, those are going to cancel each other out. Those are inverse functions of each other. They're doing inverse operations, right? The e to the power function is taking the base of e, raising it to a power, and creating a result. The natural log takes that result and brings it back to the power. So essentially it cancels out whatever e just did and brings us right back to that power. Long story short, they cancel each other out, okay? So really what we have in the numerator here is the integral from 1 to x of just 4t minus 1 dt, because the natural log and the exponential function cancel each other out, leaving us with just whatever was in the exponent, and whatever was in the exponent is just on like a regular level now, just 4t minus 1 dt. Okay, and all of that is being divided by x. So first, so that's a much simpler thing to consider. So we want to simplify as much as possible. So then let's think about this function 4t minus 1. It's linear and it's increasing because the slope is positive. So if I were to sketch a graph of it, it would hit the y-axis at -1 and it would increase very quickly with a slope of 4. And it would increase forever, right? It's going to continue to increase because of the constant slope. And so as x heads toward infinity, let's say we've got like 1 right here. So this integral is summing up, right? This integral stands as a sum of infinitely many rectangles with height 4t minus 1 times base dt. So it's summing up all of this area that's increasing indefinitely forever. This area is all positive, right? And there's going to eventually be infinitely many of it if I let x, the upper limit, go to infinity. So what I'm trying to say is that integral would eventually create an infinite amount of area. So I can safely say that the numerator will approach positive infinity as the x, the upper limit of integration, approaches infinity. Meanwhile, the denominator is also x, which is approaching infinity as well. So this creates the indeterminate form of infinity over infinity. What that means is I can use the L'Hopital's rule and take the derivative of both the numerator and denominator before trying to find this limit. So I can take the derivative with respect to x of this integral from 1 to x of 4t minus 1 dt all over the derivative of x, which is 1. And then if you remember from our fundamental theorem part 2 lesson, derivative and an integral cancel each other out. And you can take the variable of integration and plop it down in there for t. So then this is the limit as x approaches infinity of 4x minus 1 all over 1. And so as x goes to infinity, this is just 4 times infinity minus 1, which is basically positive infinity. So that was the answer for number 7, positive infinity. Moving on to number 9, this was another commonly missed question. And again, I have a feeling I know why. It's because it's got these two variables here, x and h. And the common misconception might be to treat x as the variable But I would like to draw your attention to the variable that's approaching 0 is actually not x, it's h. That means only h can be considered as a variable in this expression because it's the only thing approaching something. And so that means that we should treat x as a constant. So that's the case whenever you are looking at a limit expression. Only the variable approaching something is actually changing. Every other variable in that expression would be treated like a constant because they would be staying constant. Okay, so then the next thing I would do is just look and see what happens when I plug in 0 for h. So when I plug in 0 for h, I get x plus 0 to the 8th minus x to the 8th all over 0, which is x to the 8th minus x to the 8th all over 0, which is 0 over 0. So this is something that we could use L'Hopital's rule to determine because it's an indeterminate form right now. So we could basically take the derivative of the numerator and the denominator and then take the limit again, but we're taking the derivative with respect to h, not x. And not more than that, we're going to treat x like a constant. So the derivative of x plus h to the 8th would be 8 times x plus h to the 7th, and then technically times 1 for chain rule, because the derivative of x plus h with respect to h would be 0 plus 1. And then minus the derivative of x to the 8th, which is 0. Since we're taking the derivative with respect to h, we think of x as a constant. So then it would just be 0. And then all over 1, because the derivative of h with respect to h is 1. So let me just kind of simplify this a little bit. So basically it's the derivative, or it's the limit as h goes to 0 of 8 times x plus h to the 7th all over 1, where I'm letting h go to 0. So that'd be 8 times x plus 0 to the 7th, or 8x to the 7th. So this was the answer. The answer to this limit was 8x to the 7th. And this is the way to solve it using L'Hopital's rule. But I did want to point out one other thing, because you might have thought or noticed something about this limit. Maybe it looked a little bit familiar to you. So I thought I would remind you of the formal definition of the derivative for calculus, for a derivative function in calculus. It's this basic limit setup. So it's the limit as h goes to 0 of a function evaluated at x plus h minus the same function evaluated at x, all being divided by h. And what this was equal to, or what that is equal to, is the derivative of f at x. Okay? This limit is basically a derivative. It is in the form of the formal definition of a derivative. So you might notice, maybe I'll kind of compare them. They both start out with limit as h goes to 0. And then I've got x plus h to the 8th. That is my f of x plus h. And then I've got x to the 8th. That is my f of x. Okay, so it's f of x plus h minus f of x. And then it's all over h, just like the formal definition was. So it's the function evaluated at x plus h minus the function evaluated at x, all over the change in x, which is h. So that means that this is the derivative of f, okay, when f of x equals x to the 8th, because that was the function in the f of x spot. So then that's basically what this limit is saying. This limit is saying find the derivative of x to the 8th. Limit as h goes to 0 of x plus h to the 8th minus x to the 8th over h is the derivative of x to the 8th, which is 8x to the 7th. So you could think of it that way as well, and just take the derivative of this part, and that is the solution or the value of that limit. If you didn't recognize it, then as long as you can remember that only h is to be treated like a variable, then you could follow the L'Hopital's method and it should still lead you to the right answer. Lastly, I just wanted to make one quick comment about number 8, which was actually not a commonly missed question, but that's because I went in and gave points back, and it was specific to this particular part. So this is what the quiz showed as the correct answer. It said that these 3 expressions require L'Hopital's rule, and these 3 don't. but I kind of disagree with it related to this part right here. I think that this should actually have been over in this category of requiring the L'Hopital's rule, because when you let x go to infinity in both the numerator and denominator, this ends up being an indeterminate form. And an indeterminate form requires something special. You can't just know the value of it without doing something special. You don't necessarily need to use L'Hopital's rule, but it does require something because this is indeterminate. Whereas these two actually produced values, like this ended up being 0 over -1, which is 0. That doesn't require any special thing. This one ended up being 12 minus 1 over 9 plus 5. So it ended up being 11 over 14. So it's like it has its own value. It's not indeterminate, so I didn't need the L'Hopital's rule. This one's infinity over infinity. And granted, it will eventually end up equaling 1 because of it ends up being same over same. So we just divide leading coefficients, but still it's an indeterminate form. So I argue it should be over here. So many of you did that, and so I gave full credit if you put these for this one, 1, 2, 3, and this one. If you put these in the require L'Hopital's rule and then these two in the does not require, that's what I gave full credit for. I didn't fault you if your answer key matched the quiz, but I did go back and give partial credit. So I just wanted to make that one comment. Anyway, hope you found this helpful. And again, if you have any other questions from this quiz that was not covered in this video, feel free to email me and let me know. Thanks.